So let's take a look at a different kind of relation. And the relations that I'm interested right now are ordering relations. Okay. And best example of kind of an ordering relation is, let's say, less than. What it does is it orders the numbers. So you have that 1 is less than 2, which is less than 3, and so on, right? So that's what we mean by these. Okay. So formally, here's what we have. We have an ordering, also known as a partial order. It has to have three properties. It has to be reflexive, okay? So what we have is less than or equal to, as opposed to less than, okay? So you might have 1 less than or equal to 2, and 1 less than or equal to 1. That's the important part. That's reflexive. It needs to be anti-symmetric, okay? So what you can have is 1 is less than or equal to 3, and 3 is less than or equal to 1, right? That's just not true. So instead, it needs to be a consistent order, right? There's some kind of notion of getting bigger, okay? And of course, it has to be transitive. So if you have that 1 is less than or equal to 3, and 3 is less than or equal to 7, then from these two, we have that 1 is less than or equal to 7, okay? If you have those properties, then the relation is actually called an ordering relation, okay? And like I said, it's also referred to as a partial ordering. And the reason for that is because an ordering can actually doesn't have to be like less than or equal to that you can always compare two numbers. Instead, it might be something like subset. Okay, and the subset relation has all of those properties. Every set is a subset of itself. If a set is a subset of another and the other is a subset of the first, and they have to be equal, so it's anti-symmetric. And transitive, of course, if subset, then you have subset from the first to the third. So it's an ordering, right? But not every two sets can simply be easily compared using subset, right? So you might have, for example, 1, 2, and 2, 4. Neither one is a subset of the other, right? So it doesn't order them, right? That's what we mean by partial, right? It doesn't actually have to get all the possible combinations. Okay, so let's clarify what we mean by total ordering. And total actually says this, okay? If you have a total ordering, then if you have any two elements, A and B, right, then it's definitely the case that one will be less than or equal to or ordered, right, by the other. Okay, that will always be true. So that's the difference between an ordering like less than or equal to, where you can always compare two things. So this is total, as opposed to subset or equal to, which is a partial ordering. Okay, but again, when I think of ordering, what I think of is reflexive, antisymmetric, transitive. Right? Those are the key properties that we must have. Okay, now I brought up this word before. I kind of snuck it in, but now I can define it a little bit better. And that is that if you have an ordering and then you have two elements, and it is in fact the case that your ordering kind of lets you compare those two elements, right? Then we call that comparable, okay? As opposed to incomparable, which means that they don't relate. That's like that 1, 2 set and 2, 4 set. Okay. All right. So we have kind of basic examples here. And the first one is less than or equal to, which we brought up. That is a, quote, partial order. It's also a total order over the integers, right? And the relation subset, again, is a partial order, right? Because partial order, what does that mean? That means it is transitive, it is reflexive, it is antisymmetric, right? That's what that means. That's what a partial ordering is. It is not a total order because it doesn't let me arrange all sets. So in here I can't compare those two sets, right? They're not comparable, so it's not a total order. Okay. Substring is also a partial order. So what I might have is ABC. This is a string, right? It's a substring of A, B, C, D, E. Okay, and so is it reflexive? Yes, because every string is a substring of itself. Okay, is it antisymmetric? Also, yes, because if I have two strings, one is a substring of the other, and the other is a substring of the first, well, how can that happen, right? Because, it has to be contained inside this one, that one's contained inside the first. The only way that can happen is if they're equal. So, yes, antisymmetric. And what about transitive? Again, that's a clear yes, okay? Because if I have a substring of some string, which is itself a substring of another string, then of course the first string is the substring of that one, right? It is not a total order, right? Clearly, because for example, A, B, C and C, D, E, right? Those can't be compared, right? One's not a substring of the other. In fact, in most cases, there won't be substrings. Okay, now this is actually not a kind of a standard term, but it's one that I wanted to bring up, and that is a strict order. And we have a strict order if it is antisymmetric and transitive, okay? But it is actually not reflexive. In fact, I want it to be anti-reflexive so that nothing is less than itself, so to speak, right? So less than or equal to, that is a partial, okay? And actually, it's a total, right? Order. Less than, that is a strict order, okay? And even though in typical mathematics textbooks we usually talk about partial orderings, it is sometimes useful to at least have this concept of what it means to be a strict ordering, so I want to bring it up, okay? This is kind of the symbols that I'm going to use. If I'm talking about the numbers, then I'll likely just say less than or equal to and less than, right? Here's your partial, there's your total. This one is going to be a partial, right? I use that kind of symbol whenever I want an ordering, but I don't really know what the ordering is. And this is going to be the strict, okay, ordering, right? Okay. And I have to just confess, like I said, this is not kind of standard notation. A strict order is by definition not an order, because an order has to be reflexive and antisymmetric and transitive. And in fact, quote, strict order is not reflexive. So keep that in mind. However, all of the theorems and all of the things that we're going to say about partial orders will generally be true also about strict orders. So it's a valid concept to have in your mind.